right along. I am Brian Cantrell, VP of Engineering at Joyent, and I'm going to be presenting today on instrumenting the real-time web, and in particular, focusing on two technologies and a projection, Node.js and DTrace. So first, and I debated whether I should even have a slide on Node at all, or whether Node should simply be assumed at this point. How many of you have heard of Node.js? Okay, that's good. You're all at the right conference. Those of you who put your hands not up, you may be at the conference next door. There's always something else going on around here. Node.js is something that a lot of us have heard about. How many of you have actually implemented in Node.js? Okay, actually a decent number of you. And how many have deployed into production on Node.js? Smaller number of hands, but okay, but what you would expect given where the technology is. So a lot of you have heard about it. A bunch of you have implemented in it, and some of you have deployed on it. So this is Node.js. This is a little a snippet of Node.js. The beautiful thing about Node is that you can write a complete, somewhat useful program. The Hello World program is a web server, 6 lines of code, really beautiful. Node is, as virtually all of you know, but just to reiterate it, it's a JavaScript-based framework for building event-oriented applications. And we're seeing a lot of energy behind Node. And that's because Node is really a confluence of 3 historical ideas, or 3 ideas that have been brewing for a long time. First, of course, is JavaScript's support for asynchrony. JavaScript has got terrific support for asynchrony. And for those of you who've been doing this for a long time, and if you've been a software engineer for a long time, do you remember when you first picked up JavaScript? You know, maybe it was as early as 2000. Probably wasn't. Probably it was like 2003, 2004. You know, JavaScript was kind of a for dummies language. And you begin to play around with it, and you have that moment of strange attraction. Remember that? That moment of shame, guilt. I think I'm attracted to JavaScript, and that's not right. I have a computer science degree. I'm not supposed to be attracted to JavaScript. But as you get into JavaScript, you realize, God damn it, there's a powerful language sitting over here in the browser. This is a really interesting language. In fact, I view it, admittedly I am a kernel engineer and a C bigot, I view it as dynamic C. It is the syntax of C, but it is a fully dynamic language with great, rich support for asynchrony, including closures, which are really critical to JavaScript. It's always frustrating to me that JavaScript books don't begin with chapter 1 closures. I know this is going to be hard, but it's important. Closures are really critical for JavaScript, and they allow asynchrony in the browser, which, of course, we can leverage on the server side. So that is kind of one trend that's been brewing for decades, really, 15 years. The other major trend, or second major trend, is the fact that JavaScript VMs have become very high-performing. Thank you, V8, and V8 really kicking off an arms race now where the battlefield is performance. And we now see, depending on how you count, somewhere between 3 and 5 professionally written VMs for JavaScript on which the battlefield is performance. That is terrific. That is terrific for all of us, terrific for humanity, and really great for JavaScript, and opens up some new opportunities, and including Node. And then, of course, the third thing that you add to these 2 other ideas is if you take JavaScript's rich support for asynchrony, you put that on a rippin' fast VM, namely V8, and then you add to it the system APIs that God intended, namely the Unix APIs. Yes, God did intend that. Sorry, exactly. Apologies if I'm having to break the news to you, but that actually is God's intent. I'm here to convey that to you. He wanted me to make that really clear today in the talk. I didn't want to go on about it, but he really wanted me to emphasize it. So there it is. The Unix APIs are the APIs that God intended, and that is why if you were coding in Node, you're kind of coding along in Node, why it feels right. You go to reach for an interface, you go to reach for an API, and it's right there. And it's right there because it's just Unix, baby. But it's asynchronous. And so you take these 3 things together, and all of a sudden you can deliver new kinds of applications. And that's what we've seen, and we've seen this explosion in interest. And to me, the explosion of interest was never clearer than with Node Knockout. This is a programming competition that was held in August of 2010, and was sponsored by a bunch of folks, including Joyent. And Joyent got the opportunity to host the programming competition. Now, when I heard that they were hosting a programming competition, my first thought was like a friend that's telling you that they are contemplating a career in stand-up comedy. And you think to yourself, I'm embarrassed for you. You're going to embarrass yourself, and you're going to embarrass me. And that's where I thought, when we're hosting a programming competition, this is just going to embarrass the environment. Like, 4 people are going to show up for the program. How many people go to a programming competition? People don't engage in these kinds of things on a regular basis. I was very surprised to learn that the programming competition, which only had 224 seats, had sold out. And in fact, it sold out weeks before the programming contest, to the point where people were looking to pick up with other teams and so on. Amazing amount of interest in what was a very nascent programming environment. So there's this tremendous interest in this Node knockout competition. The competition is a weekend-long competition in which teams of 1 to 4 endeavor to build something neat and something usable with Node. And so these guys all were going to show up on Friday night and code all weekend and then be judged on Sunday. So we view this as a great opportunity. We, Joyent, view this as a great opportunity because here we had a bunch of folks that were going to organically write these new applications. What could we learn about these applications by providing an environment, by hosting them? So that's really what we wanted to understand. And one of the things we considered is, well, could we build a leaderboard for this thing? I mean, it's a programming contest. There's no kind of notion of who's ahead. I mean, it's judged at the end. But maybe we could do like a real-time leaderboard of some flavor or another. And Ryan Dahl, the inventor of Node, who works at Joyent, he had a really great idea. And his idea was, why don't we instrument incoming connections? People are going to begin to deploy these things onto the internet. The programs are going to be deployed on the internet. And let's instrument incoming connections. Let's watch where they're coming from. And let's geolocate those IPs and throw them up in real time on a world map. It's like, wow, that sounds like a great idea. That would be really pretty neat. And it would allow us to see where everyone's coming from. Now, as I have done very often in my life, I let my intuition get ahead of the data, which is almost always wrong. And I did think to myself, well, it's going to be kind of neat, but let's face it, everything's going to be coming from the Bay Area. I'm sorry to be so Bay Area-centric, but it's like the contest is in the Bay Area, everyone's in the Bay Area, it's just going to be a bunch of Bay Area. Well, let's do it. All right, whatever. There could be someone somewhere else in the world, I guess. So let's go ahead. That sounds exciting. Let's go do that. Now, in order to be able to do that, there's some technical problems that we needed to go solve. And we didn't have much time to do it. You're going to see a parallel between Node Knockout and what we did in preparation for Node Knockout. We needed the instrumentation to be entirely transparent. So we want to go instrument these incoming connections, but we don't want to have to do log analysis. We want people to be able to write their own application. We don't want them to be able to see the fact that they are being instrumented. And we want to be able to instrument pretty high up in the stack. We want to be able to see node connections. We don't want to see SSH connections and other connections that people might be making. So we really want it to be transparent and non-invasive. And these constraints are, of course, a natural fit for DTrace. So I don't want to bore you with things you already know. How many of you have heard of DTrace or know about DTrace? Some of you? Okay, great. How many of you have used DTrace or use DTrace? For how many of you has DTrace saved your ass? Let me ask that. Okay, you all are awesome. Yeah, DTrace is, when DTrace saves your ass, it's just a difference in opinion about DTrace. I remember the first moment DTrace saved my ass, personally. It was obviously very early on in DTrace's development, and you realize that this is actually going to be something that's important for ass saving. So DTrace was developed by Sun Microsystems, shed a single tear, circa 2003, by me and Mike Shapiro and Adam Leventhal. We developed it for Solaris 10, but it was open sourced along with the rest of the operating system in 2005 and has subsequently been ported to many systems, including the Mac here. Should I do a 2-second demo of DTrace? Is that, okay, enough heads are nodding that let's go look at that. And this is just so beautiful that I can actually go on to my MacBook here. Although this is going to be, okay, everyone can see that. Okay, this is going to be a little hard for me to type. Good, I got root. All right, so let's just run DTrace without any options. And here, so I'm on the Mac now. This is just running on my own Mac. In fact, you see words like this that were not in the original. If I run DTrace without any options, I just get kind of a very Unixy style help message here. What I'm actually going to do is let's instrument all I/O in the system. So what we've done is we have instrumented the code paths that initiate I/O, and I assume that if I come back over here and let's start up some I/O here, or we do it on. Okay, so we can see that we're seeing a probe now whenever we do any I/O, which is this is telling us This is the CPU and the probe ID, and this is telling us where we are in the kernel when we actually hit that probe. That's not very interesting. That we just did I/O. But with D and DTrace, I can attach arbitrary actions to it. So for example, I can say printf %s did some I/O. Oh, come on. Sorry, this is I'm like doubly blind over here. Where are you? There you are. I'm missing a quote. Damn it. This is, don't do this to me. Yeah. What's that? Reduce the font size? Is that right? Okay. Now, if I come back over here and go there, can we get someone to do some I/O? Yes. Thank you, Google. Thank you, Chrome. Chrome did some I/O. Okay, Google Chrome did some I/O. Well, okay, that's more interesting. But in DTrace, we don't have to actually just get a datum every time we do something. We can actually aggregate. Aggregation is a first-class citizen in DTrace, so I'm going to use that @ notation, and I'm going to aggregate on exec name, and I'm going to take the aggregating action to count. And now what we're going to see is when I go do some I/O in Chrome, and I'm going to go look at the latest photos from Representative Wiener, of course, see what's going on with him. It seems to get looter and looter by the day. So let's go back over here. And if I Control C, now I just see a table, Google Chrome. Now actually, let's make that a little bit more interesting by not doing I/O. Let's do, we'll do syscall entry. And then let's just add, tick, 1 sec. So what I'm going to do is, if I can, so what I've built is a little stat tool that is showing me the system calls per second by application. So what I did is aggregated syscall entry, instruments every system call entry point, aggregated by the app name, the exec name, and then added this tick 1 sec probe that fires once a second that prints that aggregation out and then clears it. So you can see you can actually pretty quickly get to something that's actually useful now if we wanted to go explore what was going on my laptop. And one thing is about DTrace, for those of you who haven't used it, in DTrace, as in good cocktail conversation, the answer to one question typically provokes the next question. Like, what the hell is MDNS responder doing on a reasonably regular basis? We're getting 500 some odd system calls per second out of MDNS responder, which seems a bit rich. If I wanted to go explore that, I could actually add a predicate here. So syscall entry. And now I want to only focus, I want to actually have a terminal that doesn't have insane settings. Syscall entry with a predicate that the exec name equals I think it was MDNS, was it capital R? Probably not. Oh, lucky guess. So now I can actually aggregate by, let's do by probefunc. That will tell me the system calls that MDNS responder is making. And I can see that we're getting a lot of K events there. I may want to understand where are we in the application when we do that. So let's actually go aggregate by user stack and probefunc. You have to type it correctly, of course. I think the terminal's killing me again. So you can very quickly hone in on, you know what, the terminal is murdering me a little bit here. There we go. Let's do by probefunc. And useStack. Okay. Now, when I Control C that, I'm going to see where I am in the application when we actually got these messages. So I can very quickly then go instrument the application and begin to dive around and so on. So DTrace is very quick for these sort of ad hoc queries and has been used a lot to debug lots and lots of performance problems. Most recently by me, anyone notice at midnight your Mac starts going nuts on I/O? Very quick, don't get frustrated about that. Just get a shell, run some DTrace, and you'll very quickly discover that Spotlight is doing all of its reindexing at that particular time. How do you discover that, by the way? Let's go back to that I/O probe, and instead of aggregating on exec name, let's aggregate on the actual file name that we're doing I/O to. Let's do args at 2 points to, and this is all documented, fi path name. Now if I go over here and click reload on my wiener scandal, which I think there's been a new photo now posted since the last time I clicked reload. It's the beauty of that scandal, keeps on giving. And now we can see what exactly we were doing I/O to. Now, the Apple guys have a harder time resolving paths than we did in Solaris, so you don't get as much path information here. But you can clearly see where it is in its cache and so on doing I/O. There's lots more you can do, and we'll see some examples of using DTrace specifically on Node, so you get a flavor for the other kinds of things that we can do. So that's DTrace, a whirlwind overview of DTrace with a lot of mistyping and some terminal conspiracies. So we wanted to use DTrace to be able to go instrument these node contestants, but how can we actually do that to go instrument these processes? How do we want to go do that? And there are lots of ways to do that. Because DTrace, you just saw me instrumenting the kernel there. When I was instrumenting system calls, when I was instrumenting I/O, I was instrumenting the operating system kernel. We could do it with the kernel, but we actually want to get higher up in the stack. And getting higher up in the stack proves problematic. It's problematic because DTrace instruments the system holistically, which is to say, from the operating system kernel. DTrace always executes in the kernel, and it's instrumenting the entire system, which is great for the ability to instrument anything, everything, but it's really complicated or difficult when you want to instrument high-level interpreted environments. You can imagine you're in the kernel looking way up at this interpreted environment, and it's very hard to make sense of what's going on up there, especially when it's being recompiled and so on, rejitted and so on. So we actually have a mechanism in DTrace to allow userland to help DTrace out and help it understand what to instrument, which we call user-level statically defined tracing, USDT. And some interpreted environments, like Ruby, Python, PHP, have added USDT providers that allow them to instrument the interpreter themselves. So if you Google DTrace plus Ruby or DTrace plus Python or DTrace plus PHP, you'll see examples of people watching code flow through PHP or watching code flow through Ruby or through Python, which is incredibly valuable, of course. As a developer, you can see inside your code in a way you couldn't do previously. But that's a little too fine-grained. You're instrumenting at too low a level. It's a little too painful to be instrumenting the interpreter in that way. And it doesn't really work in JITted environments, especially if the JIT is highly dynamic, as it is with the JVM and certainly with V8. Things are moving around too much, so you can't actually rely on that kind of methodology. So for Node, we really had to take a very different tack. And now, given the nature of what we wanted to do, we wanted to instrument, remember, we wanted to do connections. When connections are established, that's not that hot a path. This is not something, and my standards for a hot path may be different than yours. A hot path for me is once you crack like the 500,000 line per second, 500,000 of something per second, that's very hot. Then bumming cycles is actually going to be a win. If you're called less frequently than that, and certainly this path is, the cycles are probably not going to be observable. So what we are going to do is create a JavaScript function that maps to a C++ module, effectively, part of Node, that has USDT probes in it. So from Node code, and this has been pushed to the Node repo, so you can go see this for yourself, from the Node code in these paths, it makes a call in JavaScript that lands in C++ that then has the USDT probe. And we use a little trick we developed called isEnabled probes to minimize probe effect. What isEnabled probes do, and the way DTrace works, by the way, if you're wondering how DTrace operates, DTrace has zero probe effect when not enabled because you're running optimal program text. And what DTrace does is it instruments that actual program text. It changes what your program is doing. And the technique that it uses depends on the system that it's operating on, Spark or x86, or Spark, rest in peace, but x86, or depending if you're in userland or the kernel. For USDT, we added an additional isEnabled probe that allows code to conditionally say, if this probe is enabled, I want to do this extra work. And then what that actually turns into is that turns into a call that will always return false, and then we actually hot patch the text to return true in the case that the probe is enabled. That's what an isEnabled probe is. So we added some isEnabled probes to really minimize the enabled probe effect. Or rather, the disabled probe effect. So we added a bunch of probes. We added things that were of interest to Node programmers, notably HTTP server request, HTTP server response, and so on. And I've got some kind of one-liners here. With your permission, I think it would be a lot more exciting if we actually went to run this on a system in production. Exactly. This is where I begin elective surgery. I may look back on this moment as the moment where the stupidity began. But, OK, so what's actually, here we are. I am, OK, in production. I'm sure the terminal is going to give me a hard time. I'm sure I will manage to, while attempting to write a D script, I will write rm-rf/ because the terminal will have conspired against me. That is actually the failure mode. It's going to, so stick around. This could be very, very exciting. OK, so if I, there we go. This is in the East Coast, so we're getting a little bit of latency there. So let's do HTTP server request. And let's aggregate, let's just get a count here. So what we have done now, OK, so max 313 probes. What happened there? So there are, and I've just revealed the tenancy on our Node.js service. There are 313 running node processes on this box, each of which is in its own virtual OS container. We'll get to that in a little bit. So I have, in the time delta between me hitting carriage return and seeing the maps 313 probes, we went off to each of those processes and changed their program text to now vector safely into DTrace. And we're just going to get a count of the number of times we're hitting that. And we hit that over the course of that, whatever it was, 30 seconds, 10,000 times. Now, it would be actually interesting to not just, let's aggregate, let's do this. Let's aggregate on zone name. There's nothing incriminating there. So now what I'm going to do is determine who of the tenants is doing this, if I can spell zone name correctly. It'd be great if the monitor up here were working. OK. As is perhaps not surprising, perhaps is always the case, we have one tenant doing 436 ops during that period of time. And the other tenants are not doing quite as much. That's interesting. So let's actually figure out, that's the zone name. Let's actually aggregate on the, let's do the URL. How about that? This could get actually kinky, depending on what this stuff is. So now, yeah, I know, you never actually know what you're going to see when you do this. This is actually a bit gutsy. If someone's running a porn server on Node.de, we're going to find out right now. Close. OK. Wow, that's a lot of different URLs. I wonder if this is legitimate activity. Well, that's a note to myself anyway. We'll go look into that later. Yeah, this is, you never know what happens. And, in production, crazy things happen in production. Yeah, and anyway, we definitely got some interesting things going on here. And we could do all sorts of things here. And indeed, probably after this presentation, I think I will, to understand who is doing it and to what, and understanding latency and so on. I'm not going to type it in. It would just be too excruciating to watch. But if we, let me show you the example we have here. So we got some one-liners up there. The first guy is just doing something similar to what we saw. And then the second guy is aggregating based on remote address. That's what we want, right? That's what we're going to get for the, we want to get for the leaderboard. The third guy there is looking at garbage collection start. We'll talk about this in our experiences in a little bit. But one of the things we definitely learned about Node is that garbage collection really matters. It doesn't, it's not counterintuitive that garbage collection would be important. But it's very important to know when you're being GC'd. I would say, and Tim and other Node folks, excuse me. That was supposed to be Node folks, and if you take Node folks and you transpose that, you get fucking, excuse me, valued Node community. Others in the valued Node community would feel free to disagree with this, but I would say, in my experience, 9 times out of 10 when you're hitting GC, you've got a memory leak in your application. That you are holding on to memory inadvertently, and GC is running hard, but fixing GC is not the problem, and giving you more memory is not the problem. You are a drug addict, and you need to hit rock bottom. And just, if I give you more memory, it's going to go straight up your arm. Anyway, so the GC... GC start and GC done are a good way to actually understand how much this is actually affecting the actual performance of your application. And then the more interesting one down here is we're actually taking the latency from server request to server response. Now, this is complicated because Node is event-oriented. One of the beautiful things we had with thread-oriented structure, or thread-oriented programs and servers is that you could always associate work with the thread. But that was the whole point. You bound those two together. So you could watch the thread progress, and you always knew the body of work that it was doing. Node undoes that, beautifully so, and righteously so. But it means it's much more difficult to correlate the request to the response. One thing that we do is we basically rely on the fact that HTTP pipelining is kind of dead. No one really does it. So we can actually use the file descriptor to be able, HTTP pipelining on a single connection. So we can actually use the file descriptor as a key. So we watch the file descriptor that it came in on and the file descriptor that it went out on, and never mind what it did in the middle. Then we actually have the wall time for the HTTP response there. So we got a bunch of stuff that's interesting there. We put that in place. That's been pushed, by the way. That wasn't pushed before knockout, but it's been pushed now. So the USDT provider's in place for Node. How could we go meaningfully instrument these things? How could we go instrument the contestants? And for that, we have to talk a little bit, just briefly, about the virtualization model that we have for our platform as a service offerings at Joyent. We use OS-based virtualization. So we've got virtual operating systems that are running here. And just as you saw me do on the live production system, from the global zone, you can see across all of those virtual OS instances, which is actually incredibly powerful. But if we were using hardware-based virtualization, you don't have a way to do that. With hardware-based virtualization, what you're virtualizing is the x86 architecture, the instructions. You don't have that level of visibility. You can't see across machines without SSHing into them effectively, without having a connection into them, talking to the operating system. So this is a major win for OS-level virtualization. Hardware virtualization has its place too, but this is an area where OS-level virtualization is a major, major win, and we're able to use DTrace to cut across all of these guys, and we can actually see what folks are doing. So given kind of all of that background, we had an architecture for a leaderboard. We're going to define a connection establishment and teardown to be a tick. And then we're going to have a daemon that is going to instrument all of the virtual OS instances by running in the global zones of all of the compute nodes that we had running for the contest. And we'll pull that data periodically, and we'll pull it from the node. Actually, we're just going to go to the diagram. We will pull it periodically from the daemons running on the compute nodes, which I call tickerd. We're going to pull that into leaderd. Leaderd is going to merge all this stuff together, and then it's sitting behind a load balancer. These two are equivalent. So these guys are sitting behind a load balancer. Why would we put something behind a load balancer when it's just a programming contest? So something you should know about this, if this feels over-engineered, it's because I was scared shitless that what was going to happen is that we were going to launch this thing and that the leaderboard would effectively be the first Node application that someone has launched in highly visible production, and it would simply melt. And the conclusion would be like, hey, Node sucks. That's great. Awesome programming contest, assholes. It's like, oh. So this is like, and I was having nightmares about this. So we went way, way out of our way, and we were way conservative to assure success here. So in any case, we want to go build this architecture. How should we build it? Well, I mean, come on. In Node, of course. So the leaderd and tickerd were both done in Node. We have we're doing HTTP gets every 500 milliseconds. Those are the leaderd is then doing HTTP gets. Although your get will be satisfied by leaderd. The leaderd is asynchronously doing gets of the tickerd every 100 milliseconds, and tickerd is pulling data out of the kernel from DTrace every 100 milliseconds. So the latency here from you're a contestant in Node Knockout, from someone establishing a connection with your Node.js server that you just pushed, the latency from establishing that connection to seeing that pop up in a world map is 700 milliseconds. And obviously you could tune that down, but we were trying to pick a number that was basically human excitable, and that was still not going to melt this infrastructure, which is, again, my concern, my fear. So that was the architecture and the deployment. In terms of building it, we needed a libdtrace add-on for Node, so I did that. That was pretty straightforward. We needed there's a Node GeoIP add-on for Node. I'm kind of embarrassed to say this because I think this is kind of the knock on Node, is that everyone writes their own module for everything. I really, really tried to use the Node GeoIP module, but it and I have some disagreements of principle. So I wrote my own, sorry, the Node libGeoIP, but that was very straightforward. And that's obviously a very well understood problem. Then we use HTTP plus keep alive for leaderd and tickerd. I mean, one of the things about Node is it is so easy to communicate in HTTP. that you just kind of do it until you prove to yourself that HTTP won't work. It's so easy as kind of the default interconnect, even when it's got nothing to do with what you're doing. So it was very quick to build. It was about 400 lines of code for leader D, 500 lines of code for ticker D. Far and away, the most I wouldn't say challenging, but time-consuming and brittle part of this was getting Git statistics and trying to get the right goddamn options to Git log to give me the statistics that we wanted, because we also wanted to have statistics of pushes going up and how frequently people were pushing to their repos. So that was far and away the most complicated part of this whole thing, which I think speaks both highly of Node, and I think that is going to be a criticism of Git and its command line options. I think we can infer it that way. So there's some front-end challenges, of course. One of the front-end challenges, or the first front-end challenge, is how do you present this geo information visually? And now we get into we've been talking about very modern problems. Now we talk about a really age-old problem, as old as our knowledge that the Earth is round. Because when a sphere is projected onto a flat surface, you're going to lose something. Of distance, shape, size, bearing, some of those have to give. This is like CAP for cartographers. They just have to give up something. Sorry. And it must be very refreshing that you have to give up something, but it means you're always going to be dissatisfied. And there are many different map projections because that dissatisfaction is unresolvable. And that's kind of a beautiful thing, I guess. But the two most common projections are both problematic. So this is the equal rectangular projection. And I don't know how well you can see that. Hopefully you can. I mean, you can definitely see it. You can see a bunch of ice up there. There's Greenland. So this is what I would call the lazy computer scientist projection. This simply takes longitude and latitude, and let's just treat them as coordinates. I don't know. You're taking polar coordinates and just treating them as coordinates on a grid, effectively. And okay, great. Like, I appreciate that that's only one line of code for you. Congratulations. It's very terse. It also has distorted the world. And in particular, I don't know if you can see it there, Siberia is psyched. Siberia has just been like promoted to world power up there. That's that dark mass across the top. Greenland is definitely psyched. Greenland's like, yeah, I am bigger than Australia. I like this projection. Everyone else has been kind of squished. Looks like it's been hit with a hammer. It's just not very appealing. This is what Yahoo Maps uses. MapQuest uses this. This is commonly used because it's so easy to code to. Oh, this projection. Now, it's very hard for me to talk about this projection without flying into a rage, but I'm really going to do my best. This is the Mercator projection. If you can't see anything but Greenland and Antarctica, that's the fucking point. I mean, what is this, a conspiracy between Greenland, Ellesmere Island, and Antarctica to crush the world? It's like, and this is, the reason I'm so mad about this one is this is the projection we grew up on, right? This is like when your school teacher went and pulled down the map, assuming you're as old as I am, hope you are, go pull down the map, then that is the projection that was on there. And I remember at a very young age, the young Brian Cantrell feeling some incipient rage that it's like, wait a minute, Greenland is not bigger than Africa. Come on. So, the only thing this is useful for is useful for one thing and one thing only, and that is getting on a boat and pointing it to the new world and going. And that is why I think we've romanticized the Mercator projection. Great for navigators. For everyone else, it's a disaster. And Greenland. Greenland and navigate. Hey, wait a minute. The Norse were navigators. All right, this is a Norse conspiracy, but we're just going to dismiss it. All right, so the Mercator sucks. The equal rectangular kind of sucks. Then we have, the Robinson projection. Beautiful projection. You look at it, it's like, yeah, that's about it. I understand we got to give something up, but that looks so nice. It's like, Greenland, whack. Get back in your, no one even lives there, man. Go get back in your place. Africa, good, yeah, you're big prominent, Africa's there, Australia's here to play. Antarctica's kind of nicely there. It's like, the Robinson projection is a really beautiful projection. So when we talked about this, I'm like, man, let's do a Robinson projection. And I really should have checked the math behind the Robinson projection before I suggested this. Because you'd be forgiven, as I was, for assuming that the Robinson projection is, like a projection. There's actually like a mathematical transformation that takes you from a coordinate a coordinate on Earth to an X and Y offset. No. I love this. It's like, so this is a quote from the inventor of the Robinson projection, Arthur Robinson. I started with a kind of artistic approach. I visualized the best looking shapes and sizes. I worked with the variables until it got to the point where I can't read without laughing, where if I changed one of them, it didn't get any better. Then I figured out the mathematical formula to produce that effect. Most map makers start with the mathematics. Yeah, well, most map makers start with the fucking Earth. I mean, it's like, I mean, at what point, Arthur H. Robinson, are you no longer a map, you're a drawing? So I was dismayed, horrified to see, because, and actually the way I got it, but that quote, by the way, was totally backwards. I mean, it's out there, it's in the Wikipedia page, but like I started with the math, and you're like, what the fuck? It looks like this guy took different parts of the earth and just they took it at a hammer. It's like, I don't like, so it's a mess. It is math in there, but as Arthur H. Robinson tells us, the math is at the very, very end. So I was like, all right, forget it. Let's give up on that. But the thing is, like, the Mercator is so offensive. The equal rectangular is so offensive. And, I work with terrific folks who get as angry about things as I get, sometimes angrier, which is really scary. And Rob Ellis on our team stepped up and pulled it off at the last possible moment, essentially. Got that working just before the competition started. That's up on GitHub if you want to check it out. And I know after we put it up there, I know a couple of folks asked about it, so we've been trying to get it out there. He actually, I believe, ported that from Fortran. He found some Fortran code. That's where we are. That's the world we're in. So, all right, so what did this look like once we actually got up and going? And that is, if there's any way to bring down the lights or to bring up the saturation a little bit, I mean, that looks like the Earth at night, which I guess is fine. Okay, so a couple of things about this. This is running, this is during the competition, what the leaderboard looked like during the competition. I'll post my slides so you can get a better view of this. So first of all, you can take my Bay Area hypothesis and just throw that out. This is not the Bay Area. This is a lot more than the Bay Area. You'll notice so there are a lot of random colors on here. Each color corresponds to a team. What would happen is you would go to the leaderboard, and as folks came in, the lights would start to twinkle as people came to these various sites. I don't know. Did anyone play the game Swarmation? Did you see that? So Swarmation was funny. So Swarmation was one of the first ones that kind of went viral over the weekend. These guys developed it early in the weekend. Swarmation was a no knockout project. It started to go viral, and you could watch it go viral around the globe. And I felt anyone watching the leaderboard knew something interesting about Swarmation, and I don't know what to conclude from it. Swarmation is a game where you're just a little box, and you're moving around, and all the other boxes are players, and you need to make shapes that have been indicated by the game. Basically, it is everyone is panicked and no one is in charge, which is kind of an interesting metaphor for life in a lot of ways. One thing that was very interesting about Swarmation is it was very popular in Eastern Europe, in a statistically relevant fashion. And you could watch it, it's like, these guys are playing it at like 3 in the morning. They're kind of connecting to it from the middle of Siberia. But that's not what's on here. What's on here is this thing, Anansi. These guys were, this is the map reduce project. What they did is they put their JavaScript code into browser code that's being downloaded by major news sites, and this code would contact their server and ask for work to do. The idea is that you could run map reduce jobs across the planet by hijacking, and I mean that in kind of the literal sense, hijacking people's compute. So you go to a website, and all of a sudden, like, oh, wow, my lap is hot. What's going on? Oh, it's the map reduce project doing something that they want to do on something that I own. It was a little sketchy, but these guys claimed they had 6.5 million monthly uniques signed up for this before the contest started, and this was shortly after this happened. All of a sudden, like Sunday at 11 a.m. or whatever, and the world starts going nuclear. Literally, like, so you see Japan over there. Japan, they knew a guy in Japan, I guess, the eastern coast of the U.S., and then Uruguay, of all places. Who the hell knows? In any case, we saw that really melt. That was a lot of fun to actually watch that, and you could see this go on through the contest, which is really fun. So in terms of our experience with this, the leaderboard very quickly got about 1,000 active users. It could have gone a lot higher. Like I said, we were ready for the internet to show up, basically. Ready. Ready is the wrong word. Scared shitless that the internet was going to show up. We over-engineered it. CPU utilization was that, the big question about Node is, okay, but it's only one thread, and what if it goes compute bound? Yeah, well, CPU utilization was totally uninteresting. What was interesting was network utilization. Node can drive bandwidth with surprisingly little CPU. And I think that as these applications begin to proliferate, this is going to change our mental model for these applications, because Node can work the network hard with surprisingly little CPU. In terms of the reliability, it was a total champ. The Tickerd's stayed up for the entire contest, stayed up the whole week, stayed up until we ultimately took the service offline to repurpose the hardware. The LeaderD did die twice. over the course of the weekend and subsequent week. Both of those were due to memory leaks in Node. Both of those have since been fixed. As a programmer, as a software engineer, I'm used to being enthusiastic about something, wading in, and then having that enthusiasm naturally attenuated. That didn't really happen with Node. I actually got more enthusiastic the more lines of code I wrote, which is very strange for me. It actually worked like a champ. It was great. It was very fun to code in. It is one of the very few experiences I've had of like, am I done? I think I'm done. I think I just did. I think that works. Oh my God, it works. What am I going to do now? I don't know. Break it, I guess. Oh, it doesn't break. Crap. So that was great. We did have a significant issue. We had of course, it's always the things that we thought very, very carefully about and we were paranoid about were fine. The things that we kind of did as afterthoughts, like throwing in this little canvas real-time updating map to the leaderboard, was actually causing like laps to be on fire. Like that could have actually burned down a house. And in particular, the browser would crash. Aw, snap! Yeah, fuck you! So I'm sorry. That's, my doctor told me, don't bring up Chrome, don't bring up the browser crashes. We've been over this. I'm sorry. You know what? I'm not even going to go there. Let's just say that if I said aw snap when your kernel panicked, you wouldn't be so psyched, okay? It's not aw snap. It's like, let's go fix the goddamn problem. Anyway. Sorry. And it was very interesting to watch these things as they went viral. So I think that the question for us, this is like one of those, play within the play things, or very kind of meta thing, where you realize that like it was, oh my God, we were in Node Knockout all along. Like we were a Node Knockout contestant with the leaderboard. We were doing something that was very like what the other contestants were doing. Namely, we were all building these data-intensive real-time systems. And it was kind of the light went on. You're like, oh, wow, of course. That's what this thing is really, really good at. We're really good at building these data-intensive real-time systems, these web-facing real-time systems. And that's why you're seeing a lot of games, of course, in Node. But anything that wants that kind of real-time interactivity. And if you look at the early adopters of Node, they were all folks that were, if you know Matt Rainey and what he was trying to do, and Voxer, what those guys were trying to do it with Python, trying to do it with other environments, couldn't do it, came to Node out of frustration, and they found they've been able to do data-intensive real-time with Node. So this was clearly, we felt, a kind of a mega trend that we were seeing, and it's hand in glove with what we're seeing, of course, in the devices, the proliferation of devices, and what we think is going to be much more real-time interactivity. We don't have real-time interactivity on our devices today. We think that's coming. We think that Node is going to help accelerate that. And so, of course, this needs an acronym. So, fortunately, data-intensive real-time. Hey, dirt! All right, I dig dirt. So, we've got CRUD, acid, base, cap. Now we have dirt. Data-intensive real-time. And I do think we're going to see more and more things like this. I think that the important thing here is that what Node.js highlights, and the success of Node.js in this particular domain highlights, is that when you're building a real-time system that's facing the web, the problem, the challenge with those systems is not CPU by a long shot. The challenge in those systems is long latency events. That's the challenge. Be it I/O, be it remote systems, whatever it is, those events, those are the challenge. And it may seem obvious, but I think we have fixated on the CPU element of that when we talk about real-time systems. And for data-intensive real-time, we do have a different animal. So I think that, that's kind of the lesson, the big lesson to take away from this is, as a reminder, a real-time system is one in which we measure the correctness of the system based on its timeliness. If it's late, it's wrong. So that's what a real-time system is. And what wrong means, does wrong mean that someone's sad or someone died? That's hard real-time versus soft real-time, right? So a real-time system needs to be on time to be correct, and in those systems, it does not make sense to look at operations per second. We've got to lose our collective religion around operations per second. It's important. I wouldn't want to not have the data at all. It's important, but we really need to collectively focus on latency. Latency is the only metric that actually matters. And by the way, when you take latency, don't distill that into a single number. Don't average that out. Right, if you take your I/O latency, average it out, and get 10 milliseconds, what does that mean? Well, that could mean a lot of things. That could mean that your I/O is essentially like a rocket, and you have these 5,000 millisecond outliers, which can definitely happen. Or it could mean that your average, everything is at 10 milliseconds. The difference there is important. And this poses challenges to both instrumentation and the way we actually visualize the system. So, we're thinking about this problem, obviously. We think other people are going to be thinking about this as well. We think that a lot of people need to be thinking about this problem in terms of how we instrument and visualize. Here is kind of one attempt that we took at it for our Node.de service. So this is a screenshot of our real-time analytics, our cloud analytics in Node.de. What this is showing is a heat map. You've got time on the x-axis, latency on the y-axis, and we can see dynamically where our latency is. And you can see banding and so on. And we've already used this to find some really interesting things in the cloud. And actually, where are we on time? We're not good on time. We're bad on time. But actually, if folks want to, just quickly, go to, if you go to rm.no.de and go to port 8001, if you wouldn't mind. Let's see if it should be still up. It is? Okay. So what I'm going to do, okay, here is our world map. All right, thank you. All right, now stop. I mean, no, just kidding. You can keep doing it. All right, so it's very hard to see here, but what we've got is a world map up there that you really can't see at all, unfortunately, even when I click on it. But this is you guys coming in here. You're actually being geolocated on a world map that is like at night. All right, so that's hard to see. You'll have to come up and you'll have to go see it for yourself later. And what we can actually go do here, shoot. Wait, did I just close that? Chrome is like, oh, are you making fun of my OSnap? I will OSnap you, my friend. So let's go over to the analytics real quick. And what we're going to do is look at, and then I will get off the stage. So what happens? No, sorry.
You started without me, too.
I did start without you. I know. It's true. I started on time, though, let the record reflect. So let's do server operations, and let's break that down by remote IP address and latency. And what we're going to see here, if you guys are still hitting it, there you go. It's hard to see because they're all down there. But there. Okay. So this is the actual latency in real time of you guys going to that silly little Node app that just shows the actual the mix, the user agent mix. And actually, I should go over and see what our user agent mix is. And we've got the ability to drill down on this dynamically and so on. This is just a first approach. I think there's a lot more to do here collectively. I think that the important bit is that the real-time web is absolutely coming to the degree it's not already here, and that we, in both development, software engineering, and operations, need to plan for it. And we need to plan for it by thinking about the metrics that we're going to consider, and those metrics really need to be latency. So thank you very much.